Let's dive right into this explainer. Today, we're journeying to the absolute bleeding edge of modern science and engineering. We're going to explore what is pretty much considered the ultimate holy grail of clean energy, and that is nuclear fusion. You know, we hear a ton of buzzwords about the future of the power grid, but honestly, fusion, it is entirely in a league of its own. It represents a fundamental, massive shift in how we might literally power human civilization for thousands, if not millions of years to come. So, to really wrap our heads around why fusion is capturing so much attention and, frankly, so much investment right now, we first have to look at the sheer, terrifying scale of the energy problem we're facing. By the end of this century, global energy demand is projected to triple. Just think about that, 3 times the massive amount of energy we already consume today. And this intense surge is being driven by this unstoppable combination of population growth, a massive global shift toward denser urbanization, and crucially, finally getting electricity access to developing nations. As the world modernizes, our hunger for power just grows exponentially. Which brings us face to face with a rather terrifying dilemma. The fossil fuels, the coal, the oil, the natural gas that literally built the 19th and 20th centuries, we just can't rely on them moving forward. They come with this enormous, totally unacceptable cost of greenhouse gas emissions and heavy pollution. So we're standing at a crossroads. How exactly do we meet this colossal demand and pull millions of people into a modern standard of living without entirely destroying the climate we rely on? Well, here's our roadmap for today. We'll touch on the ultimate energy crisis, how we actually plan to build a star right here on Earth, the unbeatable advantages of fusion, the massive engineering hurdles in our way, and finally, how AI is stepping in to speed the whole thing up. Okay, Section 1, the ultimate energy crisis. Let's look at the pressure our grid is under and why a total paradigm shift is absolutely necessary. The next few decades, they are make or break for us. Our current grid is just being pushed to its absolute physical limits by population booms, massive new cities, and expanded access. Now, wind and solar are incredibly vital, don't get me wrong. But to actually replace the massive, heavy foundation of fossil fuels, we urgently need a totally new form of baseload energy. We need power that is large-scale, entirely sustainable, completely carbon-free, and most importantly, always on. Section 2. A star on Earth. What if the solution to this huge terrestrial crisis is to just capture the very process that powers the universe itself? It's super easy to write off fusion as just a fun sci-fi concept, but we actually see it working perfectly every single day. The sun is just a giant, incredibly efficient fusion reactor. It relies entirely on fusion to release the exact energy that makes all life on Earth possible. The whole goal of fusion energy research is essentially to create an artificial star right down here on Earth. We want to carefully bottle that exact same cosmic mechanism to produce abundant, clean electricity. So how do we actually pull that off? Well, it takes an incredibly precise multi-step process. First, you have to heat specific hydrogen isotopes up to astronomical temperatures, which creates this super hot electrically charged gas we call a plasma. Second, because literally no physical material can hold something that ridiculously hot, we have to confine this plasma inside a reactor using incredibly powerful magnetic fields. Third, we initiate a fusion reaction between 2 very specific hydrogen isotopes, deuterium and tritium. And finally, as those atoms smash together and fuse, we capture the massive amount of energy released to generate electricity. Just think about the energy flow for a second. When the deuterium and tritium collide and fuse, they form a helium nucleus, which is an alpha particle, and a fast neutron. And here is where the magic happens. 80% of the energy produced from this reaction is carried away by that fast-moving neutron. That little guy interacts with the reactor walls, creating intense heat. That heat then boils water, creates steam, and spins a turbogenerator to make electricity for the grid. So in a weird way, it's basically the most advanced complex water heater in human history. Moving on to Section 3, the unbeatable fusion advantage. Why is this specific tech considered the holy grail compared to what we have now? Well, fusion has some frankly mind-blowing environmental and safety benefits. First off, zero CO2. Literally zero greenhouse gas emissions. The only major byproduct is helium, which is completely inert and totally non-toxic. Plus, unlike traditional nuclear fission reactors, fusion produces no high-activity, long-lived radioactive waste. And perhaps the biggest deal for public perception, a Fukushima-type meltdown is physically impossible. Fusion doesn't use massive stores of fissile materials like uranium. Because the reaction needs such unbelievably precise conditions, if anything goes wrong, any disturbance at all, the plasma just naturally terminates and cools down in seconds. The reaction stops. Boom. No risk of a runaway chain reaction. But here, right here, is the true game changer. Energy density. Fusing atoms together releases nearly 4 million times more energy than burning coal, oil, or gas at an equal mass. Let that sink in. 4 million times. It even releases 4 times as much energy as traditional nuclear fission. That insane density is exactly why fusion has the actual potential to provide the massive, unwavering baseload energy we need to power tomorrow's megacities and heavy industries. And what about the fuel to actually run this thing? Well, it's wild. Deuterium can be extracted super inexpensively straight from regular seawater. Tritium can be produced by interacting those fusion-generated neutrons with lithium. Terrestrial reserves of lithium could fuel us for 1,000 years on their own. But sea-based reserves? According to the International Atomic Energy Agency, these fuel supplies would literally last for millions of years. We would basically never run out. Section 4. Grand Challenges for Engineering. Because look, if it were easy, we would have done it decades ago. Bottling a star is undeniably tough. The sheer complexity of these machines is staggering. Take the International ITER project, a massive tokamak reactor. It's made up of over 1 million components and 10 million individual parts. Maintaining those precise plasma temperatures, which are up to 10 times hotter than the core of the sun, without any physical disturbances, it requires engineering at a scale that's almost unimaginable. The materials facing the plasma have to endure extreme heat and neutron bombardment, while right nearby, the superconducting magnets have to be kept near absolute zero. It's a massive balancing act. This immense difficulty is exactly why the National Academy of Engineering has officially called providing energy from fusion one of the absolute grand challenges for 21st century engineering. Look, the physics, largely understood. Human-engineered fusion has already been demonstrated on a small scale. The true monumental challenge facing us right now is figuring out how to scale that fusion process up to commercial proportions, making it efficient, making it economical, and making it so we can actually plug it directly into our existing power grids. Finally, Section 5, AI and the grid. How on earth do we bridge this daunting gap between theoretical physics and a commercially viable power plant? Well, looking ahead to around 2026, we are actually seeing a massive pivot happening right now towards something called digital fusion. Huge tech giants like NVIDIA and Siemens are stepping into the ring, partnering up with companies like Commonwealth Fusion Systems. Their primary goal? To develop a highly detailed digital twin of the physical spark fusion machine. They're unleashing massive computing power to solve these exact engineering bottlenecks. Honestly, the role of artificial intelligence here cannot be overstated. By building an AI-powered digital twin of the reactor, these teams can use incredibly complex AI physics models and industrial software to just simulate the plasma behavior. And what this means in reality is absolutely astonishing. They can take what used to be years of painstaking, incredibly expensive manual physical experiments and compress them into mere weeks of virtual optimization. It completely shifts the timeline, rapidly bridging that gap between theoretical plasma physics and actual real-world industrial readiness. So, as we watch millions of dollars flow into these digital AI twins and we see the timeline for commercialization rapidly accelerating, it leaves us with one final, incredibly exciting thought. We have actually decoded the universe's ultimate energy source. We know how to build a star on Earth. With AI now supercharging the engineering process, the question isn't really if fusion will happen anymore. The real question is, how soon will it power your home?